If we want healthy and resilient cities, we need to understand and properly care for urban nature and the people who rely on it. When we consider the sheer number of trees and other natural infrastructure to manage, the diversity of human populations, and the increasing effects of climate change, you can imagine how difficult it is for city managers and practitioners to make informed decisions with lasting impact. Our system combines data from multiple sensors connected to the 5G network to provide key information to protect and manage nature in our cities to promote resilience. The Natural Assets team is leveraging the Rogers 5G network to pilot solutions and develop a data-driven system for natural asset management in cities. We are an interdisciplinary team led by faculty from Forest Resources Management, Electrical and Computer Engineering, and the Sauder School of Business. Natural assets refer to natural infrastructure in cities, such as trees, parks, green spaces, and other vegetation. Natural assets are also critical. They provide nature-based solutions that can help Canadian municipalities address climate change. Natural assets are also key supports for human health and well-being. To ensure our system is grounded in real-world problems, we conducted 8 interviews. These were with natural asset experts, urban foresters, conservation authority practitioners, and solutions providers to better understand how their organizations work with natural assets. We found that overall, participants outlined 3 main challenge areas: data and technology, institutional and organizational challenges, and societal issues. Within the area of data and technology, some issues include collecting inventories, user uptake, and data standardization. Participants also identified opportunities for technology to address some of these challenges. One interviewee said, "At the end of the day, what we're really trying to uncover is what we call a reference architecture for natural asset management. There's cool opportunities to test new technologies there." Envision a system that can not only identify, monitor, and assess the value of natural assets in cities, but can also generate actionable insights about how natural assets are used by people to evaluate risk and make informed decisions about investment and management. Our system consists of the following main components: ground-based sensors installed in trees and in the soil at the tree base. These are to monitor ecological activity. Aerial-based sensors mounted on an unmanned aerial vehicle, and mobile data acquired from smartphones. These are to monitor both ecological and social activity. In the last 8 months, we have done the following. We are now collecting data on both natural assets and natural asset users, and piloting data processing and analysis techniques to inform our minimum viable product. On the technical end, the solution architecture includes monitoring ecological changes for each asset, as well as proactively forecasting changes in parameters. Our natural asset system offers 2 key opportunities for technology innovation. Whether in an urban setting or a remote area, most natural assets have no direct access to power sources or well-established communication systems. Furthermore, sensing systems for natural assets typically require a large network of interconnected sensors. A solution that addresses both points can potentially be transferable into many other 5G end-use cases or applications. We've developed 3 solution architectures that can be integrated with the custom sensing devices we built. Sensing devices collect data and transmit it over an internet connection to a cloud-based service, such as Azure or AWS. In this case, sensor data and pre-processed data are sent to IoT Hub to establish device twin and other Azure-based services. Similarly, sensor data and pre-processed data can be uploaded to open-source cloud systems. In the natural asset setup, InfluxDB is hosted on UDL servers at UBC to be visualized on another open-source tool, Grafana. With the open-source tools, it is also possible to create local standalone systems, where data is collected, processed, and stored locally. This is ideal in remote areas, for example. Cellular connectivity plays an instrumental role for the remote access of devices and periodic system and machine learning model updates. Looking at the sensor nodes, we're primarily using two slightly different hardware setups. A Raspberry Pi is a computer on board that runs on Linux. The board uses a floating point system. We're using the basic version of the board with complementary add-ons. Add-on components for the Raspberry Pi board include a cellular module and analog-to-digital converters. The other type of board we're using is a cheaper microcontroller that operates in very low power settings. This board is a non-floating point system that does not run an operating system. This specific version of the board has an onboard cellular module. We're comparing the two different approaches in terms of power consumption, customizability, cost, and integratability. Before the sensing devices are deployed in the field, quality assurance testing is needed. This includes provisioning boards individually with Azure and InfluxDB. We've also manually soldered and assembled over 60 sensors into 9 sensing devices. New machine learning models are becoming more accessible for low-power, low-cost embedded systems. Currently, the main trade-offs include boards that lack the sufficient computational power requirements, which leads to higher latencies. Having custom hardware allows us to study sensor module combinations and integrations within boards. This allows us significant control over software and hardware power optimizations. More importantly, customizability allows us to tailor power responses without necessarily sacrificing latency. We have recently started looking into feeding near real-time anomaly detection models into time series data in the cloud, and comparing the latency results and model accuracy with edge compute. We installed soil and tree dynamic sensors in 4 tree locations in green spaces on campus. Soil sensors measure soil conditions, while tree dynamic sensors measure the way trees move with wind. These parameters provide us with information to assess tree health in each green space. The locations have natural variability in terms of area size, shading, accessibility to the public, and most notably, the soil type. The soil type in the open space has been commercially modified to become more suitable for construction and development projects, while the soil in the shaded area is less modified. The variability in the locations provides us with necessary building blocks to replicate this onto larger areas on campus and cities we're working with. Since we're installing soil sensors 2 feet below ground surface, we didn't want to risk reception issues, so we installed the boxes with antenna containing the data loggers above the soil sensors and just below turn level, leaving the enclosures exposed, but protected enough not to interfere with periodic grounds crew lawn mowing. The Raspberry Pi is connected to the cellular module. The board and the sensors in the ground are powered through a power bank. For sensors on the trees, installation is slightly easier, since the enclosures can be attached to tree trunks. This is the background of what's happening at a sensing device, collecting tree dynamics data. The sensing device is collecting data from 5 different sensors on a tree, and the data is uploaded to InfluxDB in Azure. We have confirmation that the data is sent to InfluxDB in Azure. The device collects data at intervals that we specify, 60 seconds in this case. While this is happening on the back end, at the front end, this data is being uploaded to InfluxDB, and you can see the different parameters being uploaded, as well as to Azure. This is the dashboard in Grafana, with data input from InfluxDB. There are 5 setups connected to one dashboard. Currently, 2 systems are fully operational over cellular IMU data from tree dynamics and commercial soil sensor compared with the research-grade soil sensor, measuring soil temperature, volumetric soil water content, dielectric constant, and bulk electrical conductivity. The other setups include air quality to measure emissions, crowd analytics to count the number of people, bikes, and cars in a space, and conversational AI to engage speakers about questions specific to the project. These setups are currently operational on Wi-Fi, not over cellular. We are working on integrating the setups into the natural asset research to ensure alignments with other groups. One key challenge in natural asset management is collecting information about tree condition across large geographic areas. Yet these datasets are critical for cities to be able to look after their trees over time. They are also important for budgeting future maintenance and planning, as well as calculating metrics for sustainability goals. The UAV we will use to assess vegetation condition is equipped with a multispectral sensor, which can detect and record changes in color in tree leaves that are not visible to the human eye. Since we are using a UAV, we will be able to collect data across a large geographic area much more easily than doing it manually. We have developed a system for streamlining the multispectral data upload to Azure. Once this data is processed, we will be able to use it to calibrate and compare the fine-scale data from soil and tree sensors. Future flights will benefit from 5G connectivity for data upload and potentially to control drones when in flight. Finally, data about people from mobile phones can help us understand relationships between the condition of urban trees and human behavior, and infer natural asset use and value. For example, do busy places show greater signs of tree stress? Do people avoid areas of poor tree condition? This demo visualization of simulated mobile phone data shows changes in density patterns of people across the UBC campus over time. We can also overlay this with data collected from the tree and soil sensors, as well as the many other data sources available across the campus. We will supplement the sensor and mobile phone data with information on individual uses and perceptions of natural assets gained from a survey distributed to diverse residents of the City of Vancouver. This will provide insight into why humans choose certain environments and how they perceive the benefits of urban forests and other green infrastructure. Natural assets are critical to cities. Our system will provide managers and practitioners with tools and information to make better decisions in the face of uncertainty. As a partner in this project, Rogers is poised to make substantive contributions to urban resilience and position Canada as a leader in the making of smarter and more sustainable cities.